Hello everyone, welcome to the 17th episode of the series. In this video, we'll talk about properties of characteristic polynomials. So far, we've learned about eigenvectors and eigenvalues, and we've learned about computing eigenvalues using characteristic polynomials. And given a particular eigenvalue, we've learned how to find all the eigenvectors. Next, I want to discuss some facts about eigenvalues. But before that, I want to recall a basic fact about polynomials. That is that a degree n polynomial has at most n distinct roots. And now this implies that an n by n matrix has at most n many distinct eigenvalues. Because if we're starting with an n by n matrix, then its characteristic polynomial will be a polynomial of degree n. So if a matrix A has the maximum number of distinct eigenvalues, that is n eigenvalues, where n by n is the size of the matrix, then the roots actually determine the polynomial. In other words, the characteristic polynomial is just given by x minus lambda 1 times x minus lambda 2, so on till x minus lambda n, where lambda 1, lambda 2 through lambda n are the distinct eigenvalues that we just mentioned. Let's look at an example. So if say we have this matrix A, and we're already given that the eigenvalues of this matrix are 1, 2, and 3, in that case, we can conclude that its characteristic polynomial has to be x minus 1 times x minus 2 times x minus 3. And upon multiplication, that gives us the cubic polynomial x cubed minus 6x squared plus 11x minus 6. And what happens if there are fewer eigenvalues? These things still hold, and we try to count eigenvalues using multiplicity, but I am not going to mention that right away. So we can say a little bit more about the coefficients of the characteristic polynomial, but for that I need to define one more quantity called the trace of a square matrix. So the trace of any matrix A, denoted by TR of A or trace of A, is just the sum of all the diagonal entries. For example, for this 3 by 3 matrix, its trace is going to be 0 plus 3 plus 2, that is just 5. We probably are not going to use a trace very often in computational purposes, but it's easy to compute, and it satisfies some nice properties. For example, a trace of any product AB is the same as the trace of BA, and for any two matrices, A and B, the trace of A plus B is always the trace of A plus the trace of B. Now that we know about trace, let's look at the next fact. So if we have an n by n matrix A and we compute its characteristic polynomial, these three things are always going to be true. The coefficient of x to the n is always going to be 1. The coefficient of x to the n minus 1 is always going to be the minus of trace of A, and the constant term of the characteristic polynomial is always going to be minus 1 to the n times the determinant of A. For example, if C is my 3 by 3 matrix, given by 0, 2, minus 1, minus 1, 3, 0, and 0, 0, 2, then its a characteristic polynomial can be computed to be x cubed minus 5x squared plus 8x minus 4. So the first point obviously checks out, that it's the coefficient is 1. The trace of this is clearly 5 because it's 0 plus 3 plus 2. So the coefficient of x to the 3 minus 1, that is the coefficient of x squared, is minus 5. And if we compute its determinant, we would get that the determinant is, I believe, it has to be 4. So the constant term is minus 1 to the 3 times 4, and that's minus 4. So we don't really have a neat little trick to describe, this 8, or actually we do, but I'm not ready to talk about this, and it's not as simple as the trace quantity or the determinant quantity. So before we get to the exercises, there's one more fact that I want to bring to your attention. So let's say our matrix A has n many distinct eigenvalues, and therefore its characteristic polynomial can be written as the product of these linear terms. If we actually multiply them out and label the trace in the determinant, we would get that the determinant of A is just the product of all the eigenvalues, and the trace of A is just the sum of all the eigenvalues of A. So this can be extended to all square matrices by counting eigenvalues with multiplicity, as I said earlier, but we're going to talk about this in the future. Okay, so let's move to the exercises now. The first problem we have is the following. We're given a 2 by 2 matrix, and we want to find its characteristic polynomial without explicitly computing it. So this is how we do it. Because A is a 2 by 2 matrix, its characteristic polynomial is going to be a degree 2 polynomial. So we write the general form of the degree 2 polynomials. Here A, B, and C are coefficients, and we need to actually find out what their values are. Now, from fact C, we know that the coefficient of x squared is always going to be 1. So A has to be 1. And the coefficient of x is going to be minus of trace of A. And we know that the trace of A is 3 plus 4. So it's just going to be minus 7. And the constant term is going to be minus 1 squared, that's just 1, times determinant of A, and that's just 3 times 4 minus 2 times 1, and that is 10. So we found out all the coefficients, and as a result, the characteristic polynomial has to be x squared minus 7x plus 10. Let's look at another exercise. And in this problem, we have a 3 by 3 matrix, and we are given that this matrix has 3 distinct eigenvalues, and 2 of them are minus 4 and 3, and we have to find the last remaining eigenvalue. So what we're going to use is the fact that the determinant of this matrix is the product of all of its eigenvalues, and we know what 2 of them are. So we just divide the determinant of this matrix by the 2 known eigenvalues, and we get the third eigenvalue to be 6. And with this, I would like to end this episode. Hopefully things were clear. I will see you guys soon. Up until then, happy learning.